That mean he's in charge of the meeting this time, Camp?
I'm in charge of the recording.
Okay.
Good
Camp's in
evening,
charge of everything
everybody.
else.
Good evening. I'd like to thank you for coming to the June meeting of the Homebrew Robotics Club of Silicon Valley. We've got a special presentation this evening. Mark Rose has been with NASA for almost 20 years and is going to tell us about the VIPER mission. It's a rover mission to the south pole of the moon, look for ice and water and things. So we got the recording started. I hereby would call this meeting to order. Thank you. So let's begin with industry news. Do we have any industry news out there? Anybody would like to share robotics? I guess
Hi, Camp. Not strictly robotics, but my nearby neighbor, Joby Aviation, unveiled the first two working prototypes of their air taxi today. And that's in cooperation with Toyota and Uber. So it's an all-electric vehicle. I think it has like 6 props that can go from fully vertical to pseudo horizontal, and sort of has a 100-mile range. So it's like avoid some of the Bay Area traffic.
Well, can you find a link on that and put it in the chat?
Sure.
All right. I guess the submersible Titanic, that was all in the news. And of course, that's ROV. Everybody became with remote operated vehicles acronym, tragedy, of course. What else? Any other industry news this evening? I've got something I can share, something I just found today. I thought it was interesting. There's a robot called Tipsy. It basically delivers drinks. Imagine that. Bear with me. I'm going to share my screen here. And so, yeah, this it's not ROS based. They seem to be using Java programming. I'll just drop this in the chat. Yeah, they've also got some hardware component to it, and they're selling it as a kit. Okay, here's the Tipsy. This is, I guess, the actual article on it. Let me put that link in the chat. Carries drinks around, delivers drinks. But I thought it was interesting because, and here's the PDF. I believe you can get at this through the article. But they've actually got a kit, Scuttle, that's called. And I thought this was intriguing, especially in relation to some of the things we've been doing in the ROS discussion group with the Lino robot. Yeah, I thought that was interesting. I'll get this one in the chat too. What else? Any more robot industry news out there? All right. Oh, I guess I've got this one too. This kind of fits into our presentation this evening. This is a link to the Space ROS community meeting. It's their meeting recorded. So NASA's actually using ROS now, and this is their community meeting recording. So if you're interested, you can check that out. Any more industry news out there? If not, we're going to get into club news now. Anybody have any club news? Oh, I do. Let's see. Yesterday evening in the ROS discussion group, we do this Lino robot. It's Lino. Lino's Tagalog for intelligence. You can look it up. Lino Robot 2, the GitHub's out there. So when you do Lino Robot, it spins up Gazebo, the simulator, and out of the box, it's like a 10-inch square, 3-inch wheels, and it's relatively easy to modify the file to make it into 20-inch square and 5-inch wheels, which is what you see here. This is Gazebo, and this is RViz. This is the visualizer, and this is the simulator. But what we did last night with Mike Wimble's help is we added a top to the Lino robot. So here you see the top is 20 inches above it. And here's the same thing in RViz, the visualizer. But that's one of the things we did last night in the Ross discussion group. So we do this on Tuesday evenings. Everybody's on the mailing list, right? So if you're interested in Ross, join our Ross discussion group. We have a good time there talking about Ross and robotics in general. So, okay. So, good evening, Wayne. Nice to see you. All right. Any more club news out there this evening? After our special presentation, we're going to have our 21st annual HPRC Challenge Phase 2. So keep your batteries topped off, and let's have a look at your robots regardless of the state at the end of the meeting. We're going to limit it to 5 minutes, but we should have some fun. That'll be after the meeting. Let's see, what's our time looking like? Okay, we're 12 minutes in. Oh, okay, we're a little ahead of schedule here.
I have club is, Cam.
Go ahead, Dan.
Okay, where's the camera? How many people are new, first time here? A handful of people, that's great. So I just want to tell you a few things about the club. We have a website, hbrobotics.org. And if you go on there, you can find there's a discussion forum. And if you do nothing else but read the forum, you're going to see a lot of very interesting topics come up, a lot of good question and answers going on. So I encourage you to do that. We have our meeting once a month. Normally we have a speaker once a month. This 3 times a year, we do double duty, which is sometimes we have a speaker, but what we have more of is demonstrations of live robots. So some people have brought robots to show you tonight after the speaker. And if you want to join, there's information about that on the club. It's on the website. It costs $10 per family per year, but we just do that to try to build up our membership and have a really supportive community. So I encourage you to look at the website. And I'm the secretary and treasurer of the club. If you have any questions about any of this stuff, ask me. Well, welcome. Glad to have you here. Back to you, Ken.
All right. So without any further ado, I'd like to introduce our special guest speaker, our own Mark Rose. He's been a software developer, intelligent systems at Ames NASA Research in Mountain View for almost 20 years. He's done work for a variety of projects and missions, including advanced telemetry display systems for manned spacecraft mission control at Johnson Space Center, tools to facilitate data discovery and data archiving for NASA's planetary data system, and the TESS exoplanet search mission, that's Tango Echo Sierra Sierra, as well as VIPER, which he's going to talk about this evening. A mission late in 2024, goal being mapping availability of water and other volatiles. So without any further ado, Mark Rose, ladies and gentlemen.
Hostess is disabled attendee screen sharing. You need to allow me to share my screen.
So Camp, we need to let him share.
Screen sharing allowed.
Okay.
And you want to put the focus on.
And make sure you put him in focus too, with the local, because we're looking at you right now, Camp.
Not that that's a bad thing. Well, let's take it.
Well. There we go.
There, that's good.
Yeah, and then are you able to share now? Okay.
Trying to. There we go. No. Trying to. Oh,
Down in the
please
middle there. should be a
allow
green-
browse access to screen recording. I apologize. So, screen recording.
On your Zoom client, do you have like this green share screen button?
Yeah, I do, but it's a system preferences thing.
Oh,
I didn't realize that the screen, that it wasn't allowing screen sharing on system preferences. So I just need to
oh, okay.
find that just for a second. And that is in, yeah, I have system preferences up. I'm just looking for the permissions sharing. Let's see.
Is this on a MacBook?
Yeah, so
Yeah,
Yeah. I'm gonna have to do it on yours because they've locked it out on my laptop. That's a new NASA feature. Sorry about that.
Haha.
Sweet. Well, you know,
While we're waiting, any robot jokes?
ooh, yes, this robot works in robot.
Never actually heard.
I thought mine would only cost $1,000.
Yeah. Let's see. Black song.
It is called 2023 PTX. This one right there.
This one?
Yep.
Okay, well, I can probably just,
You can probably just do it from the stick.
yeah,
Double click that. Oh, it's gonna do it in, you don't have PowerPoint on here? We'll see. Cross our fingers.
okay. Yeah, I've got-
Technology is great when it works.
I have some other PowerPoints that I tested this with.
Okay, that's fine.
It Depends on what all fancy you said, it's an animation.
Hey, Bob Allen, how you doing?
Sorry, I didn't check that when we got here tonight because they used to allow that. NASA locks down our laptops a lot, so
Gotcha.
as developers, we don't have administrative privileges or anything like that, so can't change it.
You're making a comment about containing sensitive documents.
I don't do any, there is classified work at NASA. I don't do any classified work. So,
It was kind of Windows hidden in your upper left.
there you go.
Hmm?
Windows, you can see the-
Oh, right.
Yeah.
Do that.
Okay.
And,
And there should be a slideshow option too.
yeah. Right.
I don't know. I don't use that tool, so even though I'm a Mac user.
Are we on Zoom yet?
Let's play work.
Yeah, play.
So yeah, Camp, you need to let me share now.
Okay, sharing's enabled, share screen's enabled.
I mean, we're sitting
Okay.
over here. Yeah, that should come on.
Um,
That's in the Zoom. You have to go back to the Zoom to do that.
yeah. Share screen. Just share the whole thing, I suppose.
Yeah, should be fine.
See if that works.
Command, tab, key.
Yeah, you have the same problem, but you can allow it.
Yeah. Oh. Not sure any password is it? Okay. Alright. So we have to record the contents of your screen, so this quick. Click, see what happens. All right.
It's still legal, so Anybody needs to know Ralph's password is sort of.
Yes, exactly. So then we had the share screen. And let's see if we can just do
You know,
this.
so-
Share. Okay.
Okay.
Everybody seeing that
Just
okay?
came on- Just came on Zoom.
Yes. VIPER, Volatile's investigating polar exploration rover.
Yeah. I'm not sure it's recording though, because you don't,
It's shown on Zoom's new record.
yeah, but it's gonna, yeah, if you do say open, it's gonna say you have to pop out of Zoom and come back in to do that. I think, I'm not sure it's recording, but
Yeah.
but it's presenting, so.
Okay.
So if you could press play, please.
Right. Okay. Good.
Zoom
Okay.
records the stream that it's pushed.
Okay.
Okay.
So sorry about the glitch there. As Camp mentioned, my name is Mark Rose. I'm a software developer at NASA. I've been there for about 18 years, and I'm currently working on a project called called VIPER. It wasn't a project called TESS, which was an exoplanet search mission. So this presentation, it gives a little bit of an overview of what the VIPER mission is, why we're doing it, what it is, and then I'm going to go into some more details about the architecture of the system. We are using ROS and we're doing a lot of robotic stuff, but it's a mixture of things that are on board the rover as well as on the ground. And then I'm going to talk in a little bit more detail about how we simulate certain aspects of the mission, because some of the things about our mission make it difficult to simulate on the ground. So we use a lot of plugins into Gazebo to do higher fidelity simulation in order to give us a greater chance of having mission success and being able to train our mission operations personnel and refine our operational procedures. Okay, go ahead, go to the next slide. So why are we doing VIPER? Well, 2 decades ago, we thought we understood the moon. We thought it was fairly uniform. All of the sites that Apollo visited and all of the unmanned missions to the moon, they found kind of more or less the same type of terrain, different geology and so on. But we thought it was surface was relatively constant. They had a very thin exosphere around it that has been studied by other missions, and that it was bone dry. All the samples returned by Apollo, all of the samples returned by unmanned missions by the Soviet Union and by China, bone dry samples. Next slide, please. However, even back in the early 60s, there were people that believed that water could exist on the moon in areas called lunar cold traps, like this paper from 1961. There are areas of the moon that are quite cold. Next slide, please. And this is because the moon has a very low inclination relative to the ecliptic. It's only inclined about 1.5 degrees compared to the 23.5 degrees of the Earth, which gives us our seasons. And for that reason, on the polar regions of the moon, the sun is always very low on the horizon. Near the poles, the sun will only be a few degrees above the horizon at maximum. And that means that any sort of topography shadows it from the sun. And if you have something like a crater, it means that the bottom of the crater may be permanently shattered from the sun. So it's never seen the sun since the crater was formed. These are called permanently shattered regions, or PSRs. They exist in sizes from real micro PSRs to craters as large as 10 kilometers in diameter. And the total area of these on the polar regions of the moon is large, over 10,000 square kilometers. Next slide, please. They're also very cold. This is a map of temperature on the south pole of the moon measured from orbit. And as you can see here, there are areas on the moon that go as low as about 25 degrees Kelvin, which is over 400 degrees below 0 Fahrenheit. In fact, the coldest spot in the solar system that anybody's measured is actually on the south pole of the moon. There are probably colder spots that we just haven't been to yet, but the coldest spot we've ever measured is on the south pole of the moon. And in particular, there's lots of regions that are below 100 Kelvin, or about 280 degrees below 0. That's an important threshold because around that point, it's cold enough that water can exist on the surface without sublimating, without evaporating, even in the vacuum environment. So if you have water deposited there by whatever process, that it could remain there from whenever it was deposited. And there are also other volatiles as well that will exist in solid form at that temperature, like hydroxides and carbon dioxide and so on. Next slide, please. And then also, so we know it's cold enough, but is there really water there? Well, missions over the last 20 years have given us hints and confirmation. First of all, the Clementine mission in 1994 had a radar experiment that had some strange phase shifting in the signal coming back that was indicative of, somebody turned on their audio. Okay. It was indicative of interactions with water molecules. So is it water? We really didn't know. We just had this strange signal. This next, click again, please. Then later on, the Lunar Prospector mission was an orbital mission that carried a neutron spectrometer. What a neutron spectrometer can do is detect the presence of hydrogen. The reason for that is that cosmic rays generate neutrons all the time on the moon, and they are normally at very high energies. But if they interact with hydrogen atoms, they can lose energy. And so, if you look at the relative energies of the different neutrons, you can tell how much hydrogen is present. So this neutron spectrometer measured elevated hydrogen levels at both poles. So we have another hint of water, but is it really water? We didn't know. Go ahead, next slide. So the L-CROSS mission was our first confirmation of water ice on the moon. This was a mission that was a piggyback on top of the Lunar Reconnaissance Orbiter mission. And in the L-CROSS mission, the empty booster stage of the rocket was intentionally crashed into a crater on the south pole of the moon to generate a debris plume. And then we had spectrographic instruments to look at the debris plume, and we measured water in the debris plume. So that was the first confirmation that there is water. But we still don't know how the water is distributed and why it got there even. Next slide. The Chandrayaan instrument then, only a few years ago, carried a NASA mission called the Moon Mineralogy Mapper, or MCube. It was a spectrographic instrument that could directly detect water, and they did directly detect water in permanently shadowed regions on the South Pole. So now we know there's water, we know it's on the surface even. L-CROSS, because with the crashing of the third stage, it might not be on the surface, but Chandrayaan proved there's water on the surface, but we still don't know how it's distributed, exactly what form it's in, and so on. Next slide. So that gives rise to VIPER. So VIPER is a mission that will launch in 2024 and go through first third of 2025. And we're going to prospect for water on human scales with a rover and create resource maps of the polar region for these water and other volatiles. Next slide. The science objectives of VIPER are twofold. First of all, we want to characterize the distribution and the state and the origin of the water if we find it. And then we also want to provide data necessary for NASA to evaluate the potential of utilizing that water and other volatiles for future missions. Because water can be used for a variety of purposes. It can be split to form fuel. It can be used for fuel cells. Even like slushy water and regolith mix can be used as shielding from cosmic rays and so on for habitation. There's lots of uses for water, and there's lots of uses for the other volatiles we may find. Next slide. This is NASA's first resource mapping mission to another world. What resource mapping is it's a terrestrial technique been used for decades in terrestrial mining, where you basically gather data to look at a resource you're interested in, explore the variability of that data, both horizontally and vertically, and then develop and test models against that data and against new data for resource distribution so that you can correlate data with particular geologic features so that you can predict where you might find the resource in other areas that you didn't directly sample. And that's what we're going to be trying to do. This gives us a variety of requirements for the mission. First of all, since it's a rover mission, it's a robotic mission, we have to move. So it has to be a movable rover, but it has to also be fairly wide ranging because we have to go to enough different spots to be able to characterize how the distribution correlates with the geology. We have to have instruments that can detect water and other volatiles while we're driving. We certainly want to detect it while we're stopped, but we have to be able to detect it while we're driving in order to be able to cover enough area. We also have to be able to sample the subsurface so that we can characterize the vertical distribution, and also so that we can find water that may be present below the surface in areas that it's too warm for the water to exist on the surface, but it's still cold enough that they could exist in the subsurface. And that means we need to carry a drill. We also need to be able to survive for weeks. And because of the low inclination, about half the time the sun's going to be below the horizon, about half the time the Earth is going to be below the horizon, so that we don't have communication. And so we have to be able to survive for weeks without sunlight and without communication all the time. We also have to investigate all 4 different types of ice stability areas that we think we might find. ice that may be present on the surface, ice that may be present in the shallow areas, but only a few centimeters below surface, ice that may be present deeper than that, up to 1 meter down, and then also dry areas. We want to characterize all 4 types so that we can correlate it with the existing geology of the region and the sunlight conditions. Next slide. So that gives us rise to the rover itself. This is the VIPER rover. It's an artist's conception. The rover is still being built. This is being jointly developed by Johnson Space Center, which is developing all the rover hardware, except for the instruments, and Ames Research Center right over here, which is developing almost all the software. There's some low-level software that Johnson Space Center is developing as well. This is the first NASA rover that's not coming out of the Jet Propulsion Laboratory in Southern California. All the Mars rovers are from JPL, but this is a rover from JSC, and the software is all from Ames. Next slide. The rover itself has power from solar arrays that are on 3 sides of the rover. You'll notice the solar arrays are on the sides because of the fact that the rover is in an environment where the sun is very low. So that means that we have to have vertically oriented solar panels instead of horizontally, like all of the rovers on Mars that had solar panels. We also have to have a warm box inside because we're going to go into areas that are maybe as cold as 40 Kelvin. So we have to have electric heaters on board. We also will be in the sunlight, and in the sunlight, it's going to get up to about 80 degrees Fahrenheit. So we have to be able to radiate heat when we're in direct sunlight. We have a radiator on top. And we also have a mobility system. We have 4 movable steerable wheels, independently steerable. We'll talk a bit more about the mobility later, but this is actually quite different from the Mars rovers that have a very passive suspension system. This has active suspension. We can turn the wheels independently and move them up and down independently. Next slide. We also have some localization and situational awareness tools. First of all, we have the nav cam on the front. The mast itself is about 8 feet high, and the main stereo camera pair is there. You can see also there are lights next to the stereo camera pairs. This is the first rover that needs lights because we're going into dark environments. On the back, we also have a stereo pair, and we have 4 cameras, 1 above each wheel for hazard avoidance, and to also check out where the wheels are in case we get stuck and we have to do a recovery maneuver. We also have situational awareness on top with a star tracker. We have a star tracker that's looking up at the star field and is comparing that with known positions of the stars and constellations. That allows us to give a very accurate indication of the rover's orientation. And then let's see, also on the top of the mast is our antenna mast. We have a high gain antenna that is used for the rapid communication to the Earth. Next slide. And then our instrument set. We have 4 instruments on board. First of all, peeking up at the top of the rover, you can see a little cover over the top of the drill. The drill is called Trident. It was developed by Brew Robotics in Southern California. On the front of the rover, sticking out the front, you can see our primary prospecting instrument, which is our neutron spectrometer. That's sitting out of the front of the rover. It's always looking down. It has a field of view of about 2 meters in diameter, and it can detect hydrogen. And that's the main tool we're going to use to detect water. We'll talk a little more about that later. The other 2 tools are underneath the rover. We have, first of all, a mass spectrometer, which is a gas spectrometer that can sniff volatiles that are gassing off, especially things that we've drilled down and brought up to the surface. It's warm enough that volatiles will start gassing off, and the mass spectrometer then can detect what elements are in those volatiles that we just pulled up. And then we also have an infrared and visual spectrometer system called NERVUS that contains both an infrared spectrometer, a visual multispectral imager, together with multiple different colored LEDs for illuminating the surface, and then also a radiometer to detect the surface temperature. Some people have said the rover looks very boxy. It does look very boxy compared to the Mars rovers, but that's mainly because of the solar panels having to be on the sides like that. And also we have the drill. Next slide, please. We also have to have a lander. VIPER is part of a program that is using landers from NASA's Commercial Lunar Payload Services program, where we are trying to incubate commercial companies to provide payload services to the moon. The same way NASA has helped incubate the low Earth orbit providers like SpaceX and Blue Horizon and so on. NASA has selected us to fly on a lander from Astrobotic Technology of Pittsburgh, Pennsylvania. That's a kind of an artist's conception of the lander. It's actually quite big. It's about 14 feet in diameter. And we'll be flying in on top of the lander, and then there will be extendable ramps that will drop down, and we'll drive down the ramps to go to the surface. After we leave the lander does not provide communication for us since we have our own high gain antenna. So we will drive away from the lander, which is undoubtedly going to land in a very dry area, and we want to go to where the water is. So we say bye to the lander, and we will not return to that site. Next slide. How does VIPER compare to other rovers? You can see Mars rovers on the top, rovers on the moon on the bottom. Most recently, the two large Mars rovers on the upper right are the Mars Science Laboratory, or Curiosity, and Mars 2020 rover, or Perseverance. You can see that VIPER is quite a bit smaller than they are, but it's larger than the earlier Mars rovers, and it's larger than the U2 rover, one of the recent Chinese missions that you can see next to it. VIPER is also faster than most of these rovers. The top speed is about 20 centimeters per second, or a fifth of a meter per second. The Mars rover top speed is more like 4 centimeters per second. And that's partly because we have to drive faster to avoid shadows and to be able to stay alive. VIPER is also the first of all of these rovers, except for the Apollo rover that was human driven. It's the first of all of these robotic rovers not to have a radiothermal heat source. The big Mars rovers have radiothermal generators to generate electricity, but all of those rovers, even the little tiny Sojourner rover that you may have remember from The Martian, that Mark Watley dug up, all of them had radiothermal heat sources to stay alive. We're dependent on our batteries and electric heaters. Next slide, please. This is also going to be one of the first missions, if not the first mission, to land on the poles. Here, this is a list of areas where there have been manned and unmanned landings on the moon so far. All of them are in equatorial or low latitude areas. There's no landings on the pole at all. So we're actually going to be going to an area where we don't actually know how easy it's going to be to drive around even. There may be a couple of missions that land on the pole before we do, because they're in the works, but some of them got delayed, so it's possible we might beat them. We'll see. Next slide. It is a new type of planetary rover. It's designed to face some unique challenges. First of all, the lighting environment is very demanding. We're going to be in permanently shadowed regions where there's no light at all. And the rest of the light is very low on the horizon. That means that shadows are very long. There's lots of reflective effects from the lunar soil because of the way that it's formed. It's also highly variable temperature-wise. We're going to be dealing with as low as minus 390 degrees Fahrenheit in a permanently shadowed region to as high as about 80 degrees Fahrenheit above zero in the sun. And we have Earth communication only about half of each lunar day. It's the first NASA lunar rover, and has an emphasis on high operational cadence and traverse speed. As I mentioned, it's about 5 times as fast as the Mars rovers. It's significantly lower cost than the Mars rovers too, but at correspondingly higher risk. And the flight software, interestingly, is split between onboard and the ground, and that has various operational impacts that we'll talk about later. But mainly, the rover itself is fairly dumb. There's even no obstacle avoidance on board the rover. So we have to be very careful how we direct it to move. And in fact, all of the motion commands are going to be determined by humans rather than by automated software, although there is a lot of automated software to help them out. It's also designed for interactive operations. This is going to be kind of a drive-by-wire mission, not strictly fly-by-wire because of the latency between the moon and the Earth. The latency is too great to be able to just drive the rover around like you would drive our RC car. but instead we'll be doing single movement operations. We'll tell the rover move 4.5 meters to here and turn this way. It'll do it automatically. Then we'll take imagery and we'll decide where to go next. So in this way, it's a hybrid of the type of robotics they do on the International Space Station and the type of robotics they do on Mars. On Mars, it's very much long sequences of commands that are executed autonomously. On the space station, with things like the robotic arms, it's strictly drive-by-wire. So we're in the middle, and that gives us some unique challenges, and it's the first NASA mission that's going to be like that. Next slide. So let's look at the science payload just a little bit. I promise I will not take too much longer on the intro, and we'll get into some more of the details of the robotics. These are the 4 instruments we have. Next slide. The first is our neutron spectrometer system. This consists of 2 different detecting tubes that detect neutrons. As I mentioned, neutrons are generated by cosmic ray impacts on the surface, and if they interact with hydrogen molecules, they lose energy. Those 2 tubes detect, one of them detects all neutrons, the other one is coated with cadmium, so it only detects high energy neutrons. And by the difference between the 2 detections and also by the total number of neutrons, we can tell both the amount of hydrogen that's present and also a burial depth up to about 1 meter below the surface. That was developed at Ames with contributions from Lockheed as well. Next slide. Then we have our infrared system and visual system called NIRVIS. This is both a combination of a visual multispectral imager and also an infrared spectrometer and a radiometer. And this allows us to directly detect volatiles like water, hydroxides, methane, carbon dioxide, et cetera, hydrogen sulfide. It also tells us something about the mineralogy of the surface and the morphology, the structure of the surface, and the temperature of the surface. Next slide. And then we have our mass spectrometer, M-SOLO. This is a gas mass spectrometer developed. It's actually both NIRVIS and M-SOLO are off-the-shelf instruments that have been adapted to space by NASA. So this was done at Kennedy Space Center in Florida. This allows us to detect low molecular weight volatiles like hydrogen and oxygen and so on, down to single atomic mass resolution. So in this way, we can not only detect the volatiles, but we can tell the difference between different isotopes. So we can tell the difference between hydrogen and deuterium or between different isotopes of oxygen. That will allow us to tell something about the origin of the water when we find it, because different origin, we don't really know exactly why the water's there. It could be left over from when the moon was born. It could have been deposited by comets. We don't really know, but knowing more about the elemental composition will allow us to test various theories. Next slide. Now we have the drill. This is the Trident drill developed by Brew Robotics. This is a rotary percussive drill. It drills down a few centimeters and brings the materials up and brushes off the tailings to form a little pile. And then it does it again. It can go down to about 1 meter. So in this way, the drill also has onboard temperature sensors, so we can tell the temperature at various depths, which will be important as well for better characterizing how much water might be available. Next slide. So how do these instruments work together within the mission? Well, as we're driving around, we'll be looking at the neutron spectrometer, NSS, all the time. And when we see that the high energy neutron drop, that's an indication that there's hydrogen present. As well, if there's stuff on the surface, we can see it with NIRVIS, or we might be able to sniff it out with our mass spectrometer M-SOLO at the same time. Also, if we're going over an area that does not have anything on the surface but has something on the subsurface, we can tell that burial depth by the NSS, the neutron spectrometer measurements. And at various times, we will stop and drill and bring up to the surface drill tailings and then analyze those. And we can see how that works in the next slide. This is an artist's conception of our drilling process. The drill and the NIRVIS and M-SOLO instruments are right next to each other on the underside of the rover. And so as the drill brings up tailings and forms a little tailings pile, we can immediately look at the materials that were in that depth layer of the drilling site. And at the same time, because we're going to bring it up to probably a warmer environment, the volatiles will start gassing off so that our mass spectrometer can sniff them and to tell us what they are. So how does this look in an overall mission? Next slide, please. So the overall mission is about 100 days or maybe a little bit more. It'll take us a few days to get to the moon, and we'll be in orbit for a few days. At that time, we will do some instrument checkout and calibration, and then we will land on the surface and exit the lander, and then begin science operations. The science operation period is about 100 days, we think. It won't be any longer than that. We're not going to be like these Mars missions that plan for 90 days and go for 10 years. And the reason is that we're a seasonal mission. At some point after about 100 days, we will get enough darkness that we will die. We can only survive for about 70 hours without sunlight, based on the amount of batteries we have on board. Our surface operations are divided into lunar days that are themselves divided into two parts. The first is a leg, or science leg, where we're actually doing science operations. And the next is a hibernation period where we have to sit in a safe haven area to await the communications to the Earth, because we're a real-time mission. We can't do operations when the Earth is below the horizon. During the hibernation period, there may be periods of total darkness up to, like I said, about 70 hours. Those are indicated as the gray lines in here. But we can survive one or two of those without a problem. And then we'll wake up at the end of that and continue science operations in the next leg. So what does a single leg look like? I'm sorry, at the end of the mission, of course, we have about 6 months post-flight to do post-analysis, and then we will submit all of the data into NASA's planetary data system, which is the long-term archive for all planetary science data. It's open to the public, free to everyone. Next slide. So what does a single leg look like? Well, from a single leg, we'll be either starting from the landing site or from a safe haven. And that will probably be it'll be in an area that has a reasonable amount of sunlight. And so that means it's going to be a dry area, which means it's not good for science. So we're initially going to have to drive to a science station. And we do that at kind of high speed mode, which we call driving on rails, where the rover drivers are in control. Science takes a back seat. They can still do science while we're driving on rails, but the rover drivers are in control because we're trying to get there as fast as possible. Once we reach a science station, we will start driving around through the science station. We have to sample about 15% of the area to give a good, a high confidence that we've adequately characterized the science station. At various points, so we're going to drive back and forth, kind of like we're plowing over the station, because we're doing a mapping mission. At various points, we'll also stop and drill. Once we exit the science station, we may have to drive on rails to the following science station. Then we'll do the same thing. At the last science station of the leg, then we'll drive on rails again to a safe haven to await the shadows and the loss of communication with the Earth until the next leg. And that's when we'll be in the hibernation period. Okay, where are we going to do this? Next slide. Well, we have to land where we think there's going to be surface and subsurface volatiles, where we can drive, so it can't be too steep, can't be too rocky. We have to have enough sun illumination to keep the batteries alive and the rover alive, and we also have to have direct communication with the Earth. So where are we going to do that on? And we've chosen the South Pole because there are areas that are promising for all four of these characteristics. So next slide, we'll look at where we were looking at. You might have to, you could stop and then move forward to the next slide and then press play again and see if it works. Or it's possible that that slide will not play.
Let's try that. Lost my cursor.
Things are going too well.
That's it.
You know, it was like really smooth.
Okay. And go to the next slide in here and then see if you can start it from there. Oh, you're editing the slide. You don't want to do that. There we go. There we go. Oh. That one. That one. See if you can play from there.
Yeah.
There we go. Okay. So first of all, we have to have areas that we know with our volatiles. The background map here is color coded based on the amount of hydrogen present. So you can see there's lots of areas that have a reasonable amount of hydrogen present. But we also have to have safe havens so that we can survive the lunar night. Those are shown in as the yellow rectangle box areas. And you can see there's not too many of those that are good safe haven locations. Move forward the slide, please. There are also a couple that have slopes that are too steep, so those are out. And next slide again. And we have some that have poor earth communications because of the topography, so those are out. That leaves 3 areas that are still available. One is near Haworth crater, one is near Shoemaker crater, and one is near Nobile crater.
So Mark,
Yeah. Yes.
these images came from a satellite?
So the terrain is based on a digital elevation model. The coloring of the main map is based on neutron spectrometer measurements from orbit. The inset maps are made by looking at the sunlight that is in those areas. So areas where the red in the inset maps are areas that are permanently shadowed. The green are areas that don't get much sunlight at all, so we think there might be shallow water. And the yellow are areas where we think there might be deep water up to a meter deep. Did that answer the question?
Yes, thank you.
Yeah, we only have one lander, so we're only picking one of the sites. So now then, which one do we pick? We've already picked, so go ahead, next slide. Okay.
When you say a meter deep, you mean there's water within the dust and dirt that goes down a meter, or do you mean really actual a meter of actual?
Oh, I mean, that's the burial depth. That's where it starts. We can detect hydrogen down to about a depth of about a meter. And so, but we don't actually know exactly what we're going to find. Is it going to be water ice? Is it going to be water molecules bound into the regolith? Is it going to be hydroxides or other things? We don't really know until we get there. But that's one of the purposes of the mission. We hope there's a lot of water ice, but we don't yet know. Next slide. So Haworth site has been rejected because it has a more difficult landing. We can only land from one angle because the landing area has to be illuminated during the landing so that the astrobotic lander with their automated landing software can avoid obstacles on the way down. So that eliminates Haworth. It's not as good a site because of the landing. And then the Shoemaker crater site had darkness and communications challenges. So we've chosen the Nobile site. Next slide. So that's the chosen landing site. The area near the Nobile crater has been named Mouton Mons after Melba Ray Mouton, who is a NASA African-American mathematician during the Apollo era. She was not one of the ones featured on Hidden Figures, but a very similar person. And so Mouton Mons is the area that we're going to be landing on near the Nobile crater.
Could I ask?
Yes.
What area will you traverse or explore?
Yeah, in a slide or two. Next slide, please. So what does a traverse for all these legs look like? This is a sample traverse. This is actually from a sample that was developed for landing in 2023. We got delayed by a year, so we're not landing until 2024. I don't have an updated traverse to show you here, but this gives you an example. The whole area here is about 3 kilometers by 3 kilometers. We plan to be driving for about 30 kilometers. This traverse is showing 27 kilometers of driving. You can see the landing site is in the middle of the green circles there in the middle left. And then the colored features here are the red is permanently shadowed regions. The green is where we believe we should find shallow water. And the yellow is where we believe we should find deep water. And then orange areas are potential safe havens. Okay, so let me see a couple other things about this. You can see that the total mission duration here on the surface is about 94 days, but only about 45 of those are active. In other words, half the time the Earth is below the horizon, so we can't do operations. The slope, the area here is fairly flat. The average slope is only about 5 degrees. And we'll drive up to about 3 kilometers away from the landing site, but the total distance driven will be about 27 kilometers. Next slide. So this is an animation. I hope it plays in Keynote. We'll see. This is an animation of what the mission might look like with this sample traverse. So go ahead and play this. Click and see if it plays. Okay, so there's the rover moving in the first leg. We're going to a science station. We will be doing moving around and drilling. And then at the end of the leg, we will need to move to a safe haven as the shadows return. So now we're in the first safe haven. This is the end of the first leg. This is the first hibernation period. As you can see, the shadows engulf most of the area. And as the shadows recede, this will be the end of the first lunar day. And we'll start science operations again in the next leg. Here we go. Okay, we're driving again on rails to get to the science station. Now we're going to do science, 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 driving and drilling until the shadows return. And now we will drive on rails to the next safe haven. This is the end of the second leg. Again, the shadows come around again. I think at this safe haven, you can see the rover completely covered in shadow for a short period of time. This is the second hibernation. There it goes, completely covered in shadow, but not too long. Now we move a little bit. Now we're in the third leg. We're moving to the science station again, do more science. This is the first half of the third lunar day. Do more science and drilling. And now the shadows are going to return again. So we move again to a safe haven. This is the second half of the third lunar day. The shadows return. I'm not sure if they're going to completely cover the rover again or not. In this safe haven, I don't think so. And as the shadows recede, we can then move to our last science station and do more science, moving into permanently shadow regions and back out. And then when the shadows return, the end of the fourth leg, and this is the end of our mission. This is where we will park the rover. We will disconnect the battery so the rover can never move again. And that's where the rover will sit. And that'll be the end of the mission. So we have 3 lunar days, maybe part of a fourth. We're planning on creating a traverse that will give us full mission success sometime in the middle of the second leg, in the second lunar day. So we'll complete all of our mission objectives, but we'll take as much science as we can get. Okay, next slide.
Can you define rails? You keep saying that.
Oh, yeah,
What
sorry.
are the
So,
train
Okay,
stations?
so well, okay, so.
That was awesome, Mark.
Yeah, driving on rails is just what we call when we are trying to drive as fast as possible. So the drivers are in control, science is not in control. We're trying to get to the science station or get back to a safe haven. Once we get into a science station, science is in control. Science will tell the drivers, I want to go there. Science will say, could you take a picture of that? Okay, could we drive there instead? Could we stop here and drill? Could you adjust the rover slightly? We want to move a few centimeters and drill there instead of here, that kind of thing. So in a science station, science is in control. When we're between science stations, we're driving on rails and the drivers are in control. Let's talk a little bit about the architecture. So next slide. So
When you get data dumps like continuously throughout Earth Day?
yes,
or- okay.
yes, we actually will have 24/7 coverage through the Deep Space Network while we're operating. And so it's a very unusual mission. That's not typical for missions. Now for manned, it is typical. But so in that respect, we're operating more like a manned mission than a typical planetary mission.
I'm thinking if things go bad, it's likely you'll still have data.
Yes, we will get data continuously because we have to have the data to make the next driving decision. So our architecture is quite complicated. On board the rover, we have software on board, but it's fairly basic. It's for low-level control. There, as I mentioned, there's not even any obstacle avoidance on board. There is some amount of automated recovery. For example, if we get into a position where the rover, we may drive into a communication shadow, and we don't know it because we can't see the topology way off on the horizon. So we drive into a communication shadow, and all of a sudden the rover loses communication. We do have software on board that will detect that and will back up to the last point where we had communication automatically. So there is some amount of recovery automated on board, but it's very, very minimal. The onboard software is written in C and C++ using a framework that's open source by NASA called Core Flight Software, which is designed for running on flight hardware with real-time operating systems. So we have a couple of one radiation hardened processor on board and one radiation tolerant processor, and all of flight software is written in C and C++. Then we have a 1.3 second radio link delay to the Earth based on the distance between the Earth and the Moon. And now we hit the Deep Space Network. That is a collection of 3 different sites that NASA runs to give us global coverage of communications to the rover. They have sites here in California, in Southern California, in Madrid, and in Canberra, Australia, to give us global coverage, or almost global coverage. The Deep Space Network itself has a ground latency of several seconds. So that's on top of the Earth to Moon latency. So by the time we get the telemetry, or by the time we send commands, it's actually several seconds from the time it was originated. Then we get to our telemetry and command system. This is where we have our console user interfaces. We have telemetry display, the ability to invoke commands. We have the ability to view time series data, and we have a time series data archive. I'll talk a little more about that later. On top of that, we have external systems that are running some of our instrument software on the ground to do instrument software calibration and derivation and so on from the raw telemetry. And then we get into ROS. So we do have a large ROS component. We have, in particular, rover ground software on the lower right is a lot of automated robotic software. We do stereo processing, we do visual odometry, automatic hazard identification. We do terrain registration based on generating point clouds from stereo images. We can register that against stored digital elevation models to give us a correction of our locations. We also have quality metrics on this, and also the ability to do path planning. So if the driver wants to drive here, we can automatically generate a path there. They may not take that path, but we can supply that path to the drivers.
Sorry,
So-
question. So, and then the DDS software, does that control the drill?
Oh, no, DDS is the underlying communications mechanism that ROS 2, we're using ROS 2.
It's a very bad joke, I'm sorry.
Oh, sorry.
Competing with Mark.
So the rover ground software is designed to be like driver assistance, kind of like the driver assistance in an automated vehicle, you know. So, but on the other hand, we are actually driving using a different tool called Verve that's developed at NASA that also talks ROS, and that's our driving tool. So human operators will actually choose the next drive location and be able to see all the situational awareness within that Verve driving tool, but it does talk ROS. We also have some mapping and GIS services that talk ROS and get information from both the regular telemetry coming straight down from the rover, as well as derived telemetry coming out of our ground software, and they create map layers for a view in web browsers for the console operators to look at. And we have planning tools that deal with the mapping and GIS services to allow us to insert plans, to insert suggested traverses, and we also have other tools to allow us to manually correct things like the rover position. If we think that the automated correction is not good enough, we can manually correct the rover position based on visually looking at where we are. Okay, next slide. A lot of this is based on open source software. So we're using core flight system, as I said. We're using a telemetry and command system called YAMPS. It's an open source project available on GitHub, developed primarily by a company in Belgium in Java. We're using a system called OpenMCT for telemetry display for most of the console positions. That's a NASA open source project, also on GitHub, for display of telemetry information, including plots and images and map layers and so on. And we're using ROS, of course, and also OpenCV as part of ROS for doing visual processing. We have Verve, which is our driving console, is also open sourced, available on GitHub. Actually, no, it's available on, it's not on GitHub, it's one of the other places, SourceForge, I think. We're using a system out of JPL called MMGIS for GIS systems. That's also open source. We're using a non-open source tool called ICER, which is an image compression library from JPL that's used by the Mars missions as well. That has certain advantages over other image compression libraries, which is why we're using it. And then we're using something called the AIM stereo pipeline, which is also open sourced for stereo image processing. That was originally developed for offline processing of orbital images, but we've done quite a bit of work on that to make it work in a more real-time mode for the VIPER mission. Next slide. And just a couple of pretty pictures of our software. This is an example of a telemetry display using the OpenMCT tool. As you can see, we can show plots, we can show tabular display as well. We can show canned images with telemetry next to them, as well as live images, and we can show map layers. And also there's a timeline view at the bottom. This is called OpenMCT, or Open Mission Control Technologies tool. It's a tool for telemetry display. I've often thought that we haven't done this yet, but I thought writing a ROS plugin for this would be very useful because it's a really nifty display system. It's a point and click way of setting, you basically just do drag and drop to create these displays. So NASA has a lot of telemetry display tools, but most of them involve creating the display either in code or in a representational language. And this is actually one of the first tools where you can just drag and drop and create displays. Next slide, please. Another pretty picture of our rover driving console. The rover driving console is built on the Eclipse framework. It's in Java using SWT, and so you can create a variety of views, and it comes with a variety of views. This is one view, and just showing a few aspects of Verve. As you can see, we can see live imagery on the lower right. We can see a 3D view of the rover model. That's together with hazard maps. The reddish areas in the hazard map are areas where we don't want to drive, mostly because of the angle of the slope. So there may be a crater there. There may be a rock that's too tall for us to drive over, so on. The driving tool is the puck in the middle left there. You can drag that around to say where you want to drive to, and then you can drag the orange arrow there to say what orientation you want to end up in, and then just say drive, and the rover will go there. And then the big yellow arrow on the right is the sun angle. That's important to know for the drivers, because we have to have one corner of the rover pointed at the sun most of the time, so that we have two solar panels both pointed at the sun. And then there's some information at the bottom, which is the status of commands that we've sent, imaging or other commands. From Verve, we can request images, we can move the cameras, we can change the orientation of the rover, etc. Next slide. Okay, so what I want to end up talking about before we get to some pretty pictures is some simulation tools that we've developed to help the mission gain success. But let's first talk about some challenges from the mission that require good simulation. Next slide, please. So the big operational challenge that we have in VIPER is that the rover is idle about 90% of the time. The reason is that because of bandwidth limitations, we can only take images. We can't have video. This is not a mission where we're going to have live video. We're just going to have individual images. We can send the rover a command to move, and it will typically move about 4 or 5 meters at a time. So let's say we move 4.5 meters. That takes about 45 seconds at the nominal drive speed of 10 centimeters per second. That's half of our maximum drive speed, but that's our nominal drive speed. So we can drive for 45 seconds, and then we can take images automatically and send them down to the earth. But taking those images takes several seconds. It takes several seconds to just capture the images and compress them. It takes several more seconds to send them to the ground, and as well as the transmission and ground latency. By the time we get them to the ground, it may be a minute and a half later after we've sent the drive command. So now we start the ground processing, and we do stereo processing to generate point clouds. We do the visual odometry to correct the pose estimate that's come down from the rover. On board the rover, we have a pose estimation based on an extended Kalman filter that integrates the star tracker and the IMU and the wheel encoders. But we augment that on the ground with visual odometry based on generating point clouds from adjacent from stereo pairs to see how far we've actually driven. And then after all that happens, after we generate hazard maps and the point clouds and so on, we show this information to the drivers. Now they make a decision of where to go. And then the drivers decide where to go and send another command. That whole process can take 4.5 minutes. And we're driving for 45 seconds. So 90% of the time we're idle. Now the problem with that is that even driving at 10 centimeters per second, if you're idle 90% of the time, now you're only going at 1 centimeter per second. And the shadowing on the moon varies in speed between 0.1 and 1.8 centimeters per second. So almost twice as fast, up to almost twice as fast as we can drive. That means that we have to be very good at planning to make sure that we don't drive into a situation where we're going to have difficulty avoiding shadows. But secondly, any interruptions in our driving, any hiccups, any places where we get stuck and we have to back up and go around can affect our ability just to stay alive because of the way the shadows move. So next slide, please. So there's 3 problems. First of all, we have to accurately predict where the shadows are moving. And because of that, we need high resolution digital elevation models, 5 times higher resolution than are available from orbital tools prior to this mission. I'll talk about that in a minute. So we need to be able to generate high resolution digital elevation models. Also, the rover expected speed is very sensitive to obstacles we find. So we have to be able to simulate obstacles so that the drivers can get used to avoiding obstacles and going around obstacles. And so that drivers can be trained well. And that requires us to have synthesized terrain that is realistic, because we can't see these obstacles from orbit. The highest resolution imagery we have from orbit is about 1 meter per pixel, but we are sensitive to objects down to about 4 centimeters. So we have to be able to simulate small obstacles and terrain features. And then finally, if we get into anomalous situations, like if we get a hiccup in communications or a hiccup in shadowing, that could cause us to get stuck and then possibly die because we get overrun by shadows. So that requires us to do very risk-aware planning. Next slide, please. So how do we do this? Well, the best digital terrain models we have right now are 5 meters per pixel from the LOLA instrument on Lunar Reconnaissance Orbiter. That's a laser altimeter. So they shine a laser down, bounce a laser off the surface, and based on the time, they know what the distance is. They know the orbital ephemeris. So now they know the height, the altitude on the surface. But that's only 5 meters per pixel. Next slide, please. Also, it's not complete coverage. This is an example image showing where the actual LOLA shots were. That's where they actually fired the laser. So you can see there's a lot of terrain that's not covered. And so much of the digital elevation models for LOLA are interpolated. So they may be even less resolution than 5 meters per pixel. Next slide. We do have good high resolution imagery though. This is from the LROC camera on board the Lunar Reconnaissance Orbiter. It's a very high resolution camera and has a resolution of about 1 meter per pixel. So what do we do to get a higher resolution than we get from LOLA? Next slide. We've developed, well, I haven't developed, smarter people than I have developed tools to look at images of the same area at different sun illuminations and look at the different shadowing and then infer the terrain that had to be present to generate that shadowing. And that allows us to generate digital elevation models at a resolution equivalent to the visual imagery, so 1 meter per pixel. Next slide. So this is an example of the 1 meter per pixel elevation model that we can generate. That's much better than the Lola model. So now we have a 1 meter per pixel, but the problem is that that's not even fine enough because we don't see all the rocks and we don't see all the craters. So what are we going to do? Well, we have to simulate that. So next slide. We come up with models of rock and crater distribution. And this is from literature, existing literature of people that have studied this from orbit and also from in situ images from Apollo and landers. And so we take those two models and then we artificially inject new craters and rocks. Okay, next slide.
Mark, can I
Yeah.
just do a time check? We're at
Yep.
8:15.
Yep.
We talked about getting into the robot challenge at about 8:30.
Yes.
So
So
wrapping
I
up
think
in
I have about
2.5.
8 minutes left. And if that will be enough time for Q&A, so okay. So we also have to adjust for crater age. So we have a crater age model. We put craters of different ages and we give them different slopes based on the age. Next slide. Now we have to add rocks based on the craters because most of the rocks are from crater ejecta. And that also varies by age. So we have ejecta models. Next slide. And then we have to be able to simulate the images we're going to get in Gazebo. So we have to develop models for basically when we come up with everything, now we have to make it look right in Gazebo. So we do that by comparing with what actual rocks look like in simulated lunar lighting environments. And we adjust our models until they look the same. Next slide. So what's the result? The result is that this is a completely simulated image that where some of the craters are there from the digital elevation models and some are entirely simulated, and all those little rocks there are entirely simulated. But that allows us to give a reasonable impression of the drivers of what they're going to see on the moon. But it is fake. Let's be clear about that. Next slide. Another example image. This is actually from Gazebo showing the rover model on the moon. You can see the rover itself is about is a little over 2 meters wide. So all of most everything you see here is simulated because of the fact that it's smaller than a meter. Next slide. Another visual image. Next slide. We also have to have risk-aware route planning. So we basically plan different routes and then we simulate them by injecting artificial anomalies on the routes and seeing how that affects our success or failure. And so we select the routes, select a traverse based on this to give us highest probability of success. Next slide. Okay, now we just get a few pretty pictures. Next slide. Actually, this is you can play this a little bit. This is a artist's conception of the rover as it might appear on the moon. Actually, maybe just skip this one. Maybe just skip this one. Okay, you can probably just click right here, or might go to the next slide. There we go. This is an example of how the ramps are going to extend down from the lander, and we'll be able to drive down to either pair of ramps. We just did testing of this in Ames this week, actually, based on a simulated lander. Next slide. The lander also has cameras on board that we'll use to augment our onboard cameras for egress. Now, we don't have the real rover, but we do have some test rovers. This is a rover called McGrew, the Moon Gravity Research Unit. It is built to be stripped down to be only about 1/6 the weight of the real rover, so that it behaves on Earth the same way the real rover will behave on the moon. It only has the motors and the suspension on board mainly. And as you can see, it has a big tether back to the power, and the rover software is actually not even running on the rover. Next slide. This is an example of the suspension system. We can independently control all of the wheels turning and also moving up and down, and that will be important for some of the gates that we can level the rover in this way. We can also even scooch the rover along or even walk the wheels along if one wheel gets stuck.
What material is that made with, Mark?
I think much of that is aluminum, I think, but I'm not positive about that. I'm not as involved with the rover hardware design. Sorry about that. Next slide. This is an example of the rover in a lab at Glenn Research Center in Cleveland. This is the slope lab. As you can see, this is lunar simulant soil where the rover is driving, and we can independently control all the wheels, and we can drive in soil that we believe will be the same viscosity and resistance characteristics of the moon. We can even do special gaits like this swimming mode, which looks a little bit like a breaststroke. This is designed to allow us to continue to move even in very low friction environments. There's actually even some more advanced gaits that they've developed, which involve both doing swimming as well as lifting the wheels at the same time, that are more efficient energy-wise. Next slide.
So like our home robots, the wheel odometry is just about useless.
Well, that's one reason why we do visual odometry. But on the other hand, if it's fairly flat, there is not a lot of slippage. There is some slippage though. This is another example of at the slope lab where we're testing driving up a steep slope. They're big trays where you can put the lunar soil simulant, then hydraulically raise them up to a desired angle. Next slide. And people are placing rocks and measuring them very carefully for different types of tests. Next slide. As you can see, this is an example of using the suspension to level the rover even though we're on a slope. Next slide. And this is a test of driving over an obstacle here. This is not using the suspension right now. Normally we would be using the suspension in active mode, and so the wheel would pop up automatically based on what's happening. But this is just one of the tests that they run. Next slide. Actually, let's skip this slide. This is kind of interesting, but we can skip it. Next slide. We have some software on board to automatically detect when the wheels are embedded and tell us that. This is a picture of the egress testing I mentioned. This is a simulated lander with the ramps, and we drive down the ramps slowly. Next slide. Another view of egress testing. This is a high-speed view of a very slow test. We drive down very slowly when we're going down these ramps. Next slide. And so the past decade or so of our observations have given us a much different view of the moon. We know there's water there. We don't know exactly how its characteristics or distribution. So that's what we're going to do on VIPER, is to find that and model it. And that's the last slide. Questions? And I went over by 8 minutes.
How long can you survive no sun?
About 70 hours. And the next question was, why don't we have a radiothermal generator on board like the Mars rovers do? Two reasons. One is we're a low-cost mission and they're expensive. And two is there's not a lot of plutonium. And so the radiothermal generators are generally reserved for outer planets missions or the Mars missions.
The other isotopes aren't interesting.
Well, I'm not an expert in that area. It's just basically there are not many there's a limited supply of suitable material for building radiothermal generators. And so NASA is being careful with it. So since we can operate without it, we are. There is actually even an outer planets mission, the Jupiter mission. It's in orbit right now. No, it's in orbit right now. I forget the name of the mission. I'll have to look it up. But they're actually using solar panels. It's the first outer planets mission that just uses solar panels. But all of the other outer planets missions, New Horizons, that went to Pluto, and it's out in the Kuiper Belt now, and Cassini, that was the most recent mission to Saturn, and other asteroid missions all had radiothermal generators on board. But it's mainly for cost, and also because of the fact there's just not that, NASA is parsimonious about allowing missions to use radiothermal generators.
Mark, you mentioned disconnecting the battery at the end of the fourth leg.
Yeah.
Why wouldn't you stay connected?
That's an interesting question. I don't have a good answer for that, but I believe the fact that if the battery stays connected, then it's possible that it could be commanded by somebody else, not by NASA. And I don't think NASA wants that, and so they want to disconnect it. It's part of it, but it's also that's a speculation on my part. So don't quote me on that. The other speculation is just as part of the we have to file a planetary protection plan so that we limit the disturbance we do on another world. And so by ensuring that the rover can't accidentally drive, and again, if the battery warms up, there's some software glitch and it just starts driving, is probably part of our planetary protection plan too. Now we do encrypt all our commands going up, so that also helps to keep somebody else from driving it. But I think it's mainly for the planetary protection plan.
Mark, what is
Yes.
your degree and how many people are working on the VIPER project?
I have a degree in computer science. So I'm not a scientist and I'm not even a roboticist. I don't work in the robotics area, although I do some ROS work, but I'm not a roboticist by training or by trade. But I've been a software developer for a long time, as you can tell by my gray hair, ample gray hair. How many people are working on the VIPER project? I don't have a good figure for you. I'll have to look that up because we have, it's kind of depends on how you count people. Because for example, the pictures of testing in the Slope Lab at Gold Research Center, well, people at the Slope Lab work on lots of projects, but part of the time they were working on VIPER for us. So if you count them or not. There are people at Johnson Space Center that are helping us out with instrument testing, but they also work on other missions at the same time. So how do you count them? So if we counted everybody, there can be hundreds of people. But in terms of people that are dedicated to VIPER, we have a much smaller group at Ames. Well, in the ground data system software, we probably have about 20 people. The rover ground software and rover flight software has another tens of people. This is the largest project in our division, which is the Intelligent Systems Division at Ames. And the Intelligent Systems Division as a whole is probably a couple hundred people, and we're the largest project. But then we have people at Johnson Space Center that are actually building the rover and doing low-level avionics software. And we have people at Ames that are working on the both the neutron spectrometer, NSS, and the infrared and visual spectrographic system, NERVIS. And they are, that's several scientists and several engineers in both those teams. And then we have people at Kennedy Space Center in Florida working on the mass spectrometer M-SOLO, and that's a few scientists and a few engineers on that.
Dillo has a question. Dillo, go ahead and ask your question.
Yeah, hi, can you hear me?
Yes.
Yeah, okay, hi. So is this going to be a solo mission, or is this going to be done with, I've noticed that there's development on things like the flat pack rovers and cadre and things like that, and I was wondering if this is going to be a solo mission, or would there be any cooperation with other rovers?
That's a good question. This mission is kind of standalone in that it has different goals than some of the other robotic missions to the moon, which some of them are much more proof of concept than ours are. We're actually really planning to be a resource mapping mission. Some of our instruments are going to be flying on other missions, though. There's a mission with a rover from Carnegie Mellon that is, I don't remember the name of that mission. Oh, I'm sorry, I apologize. Mental block. I don't remember the name of the mission. It's flying on another Astrobotic lander, but a smaller one than ours. And that's, it's a experimental rover because it's student run, grad students are running that mission. But that's going to carry the same neutron spectrometer and some of the other instruments. There's also there's a non-rover mission to the moon that will land on the poles from Astrobotic that's flying on a smaller lander called Peregrine that will have both the neutron spectrometer, the nervous spectrographic system, and the M-SOLO system on the same lander. So much like VIPER,
Yeah,
except they don't have a drill,
Right.
but they're not going to be a roving mission, so they're going to sit at one place.
yeah.
However, I'm
One
very
more
excited about
quick question. One more
Good.
quick question. Is you mentioned about like disconnecting the battery and parking the rover. There's no chance of an extended mission
No,
where you would
partly
keep
because-
rolling like Curiosity or
No,
just
I
going
mentioned-
for
I
years and
mentioned that
years and
before.
years?
No, I mentioned that before. We're definitely not going to be like the Mur rovers, Spirit and Opportunity, nor like Curiosity and Perseverance, because of the fact that our mission is somewhat seasonal. At some point after about 100 days, the sun will get low enough on the horizon because of slight changes in the moon's orbit, that, as we go around the sun, that we will have too long a time without the sun and our batteries will die. So
All
we're
right.
definitely only going to be about 100 days.
Let's,
Okay.
let's get one or two more questions in, and then we need to move on to our
Yeah,
challenge.
Mark, quick question. What if your lander is not flat and you land on a 20 or even 30-degree angle and you go to deploy your ramps and your ramps are not level and or the ramps are landing on a rock? How do you get the rover off the lander?
Oh, that's a good question. So we actually test. So I had a picture of egress testing at Glenn Research Center that was done last year. We just finished a round of egress testing at Ames, and they test not only flat situations but also inclined situations. They will incline the lander by up to a certain number of degrees. I'm not sure if it's 30 degrees or not. But I believe that the lander, that contractually, we're not supposed to land on an area with more than a 15-degree slope. But then we also have tried various other things where we put rocks underneath one or more of the lander ramps. And we also have tried splaying the lander ramps out or in and having that be part of the test. So we've tested in a variety of situations that we believe to cover the range of situations we might see. Now, could we get into an unforeseen situation where we land at steeper than that and we're unable to drive off the lander? That's possible, but that's one of the reasons why we have two lander ramps. So if one ramp set is blocked, we can go down the other set. We can drive either forward or backward. We have cameras on both ends. And in fact, I didn't mention this, but we either have to drive most of the time facing the sun. Oh, so we have to have a corner facing the sun, and that means that we basically are driving mostly either toward the sun or away from the sun. We like to drive away from the sun because that means our nav cameras are in front. But for part of the time, based on the traverses that they're planning, we will have to be driving toward the sun, which means we'll be using the aft cameras. And those are a little bit wider angle than our cameras in front on our nav cameras. So they're not quite as good for the stereo processing and odometry, but they still are serviceable.
I see.
James Fellon, you have a question?
Yeah, why not do more autonomous driving and take advantage of the Mars experience, especially given your limited drive time?
That's a good question, and that's mainly for cost. It keeps the cost of the rover down, not to have all the autonomy on board.
We've got to cut it off here just to move on to the next thing. That was fascinating. Thank you so much.
Thank you very much, Mark Rose.
See some of the
Yeah.
robot demos.
Yeah.
The first one you might find really interesting.
Okay.
Al, are you ready?
Yes. So we'll have to fiddle with the camera. Al, can you do that?
Didn't turn you off today. Still have power.
Yeah.
Is Al Margolis coming up?
Al's coming up.
Al Margolis, ladies and gentlemen.
Darren, Sikan,
Hang on one second.
Roberto, why don't you come up? Move this slide.
Yeah,
yeah. Let's move this a little bit because you can't fall up the edge if there's no edge.
It's okay. I may not even move. So, well, okay. I am Al Margolis. I've been with Brew Robotics forever. I'm
Lower the
web
camera,
master,
lower the
actually.
camera a bit. We can't see the wheels.
Well, we'll move it around. We'll look at it.
There you go.
I'm also the Director of Operations at the Moffett Field Museum. We're right by Hangar 1. It's a great place, and I have recently started a STEM program. I've been doing STEM before it was called STEM, and we're doing a clinic sort of approach. Bring a bunch of people together and work on projects. Some of the projects will be museum projects. People come and work on their own projects. If you go find our website, it's moffettfieldmuseum.org. Look for the STEM link, and you'll see what's going on. You can send me an email. We've just kind of got started. Our first thing, we are doing it's a marketing event, and I'm also in charge of marketing, called County Fair on the Moon. That is going to occur the week that includes July 20th. Anybody remember the significance of that? July 20, 1969, the first human moon landing. And one of the things for our STEM month, we had kids flying drones. What I want to do for that week is we're going to let kids drive VIPER. We have this large table area. They're going to drive it on there. And if everything works, we will have an augmented reality sort of thing where they'll get a video of their driving on the moon, layered onto the moon.
That's awesome.
So it's a fun thing. So I've got a team of people who are building the VIPER and another team who are working on the augmented reality vision stuff. And we can use more help. We've got more projects. This is kind of a kludge. Everything you see here was at Amazon about 2 weeks ago. And it actually moved a little bit. I'm going to give it a try. We'll see. And I have the parts for our version 2, which will be for next year, which actually has a more independent suspension. And, we're working on we'll have other projects for the museum. So what we did, building robots is hard. We all know that. And having, they're basically 12 degrees of motion, I think. We've got 4 spinning, 4 turning, and 4 arcing. Building all that for a new group would have been quite a challenge. And so I didn't want to try. But every RC car has a motor and steering. So what we've done is we've taken 2 of them, glued them together essentially. Today was the first time we actually got this far, 3D parts. This will, when fully implemented, we've got 4-wheel drive, just 2 sets of motion independent and 2 steering, but we'll be able to do the diagonal steering, diagonal driving. Only one of these was reacting for some reason.
See if you can get a phase 1.
But I can drive. So this is all off the shelf. See, Chung here's just drew this today. We're going to swap out the wheels for a little bit more realistic wheels. When it's running at the museum, there'll be an Arduino running the motion parts and the Raspberry Pi for communication. And the drivers, mainly kids, will have a little mission control station, basically driving by a joystick, and they'll have vision. Yes.
Can you introduce your team that you brought here today?
Yes, I did. Okay, this is Si Chung. She is a high school student with looking towards a career in engineering, and we have a bunch of high school kids working. This is Darren, who's a recently minted Master of Engineering in Mechanical Engineering, who just went to work for a large fabricator. This is Roberto, hasn't joined our STEAM program exactly, but he's a friend of the museum who runs what I will call a boot camp, Silicon Valley boot camp for students from Brazil. And he brings groups of them through the museum every 6 months or so. And he's maybe joining us in some way. We've got like a half dozen kind of regulars for our first few sessions. And like I say, we want more people, we'll have more projects. And the idea is we will have museum projects, stuff we want to build for the museum, come in, help build those. If you have your own project and you want some help, bring it in and we'll try and help you. If you want to get started in robotics, we'll have some kits. So, we'll have some Arduino starter kits and give some hand-on experience and how to do that.
Very good. Thank you very much. Al Margala is in the model VIPER. That's awesome. Do we have more show and tell there at Maker Nexus?
We do. I have one.
But wait,
Yeah,
there's
Mark,
more.
how's there over here? Mark, you can bring it up if I'm set, if I'm ready now, yeah, pretty much connected up. Okay, this is Droid
Mark
Bot.
Johnson, ladies and gentlemen.
I've been here before, and this is a very much revamped version of what is called Droid Bot. Has a long history with the club because it came from one of the guys. It's been through two of the people in the club. One is no longer with us, but I inherited it and making good use of it. Now I've converted it to over so that it is a ROS 2 system. Sorry for the poor graphics here, but I just nobody's going to see it out there. But anyway, we basically have a Raspberry Pi 4 running Ubuntu Linux 2204. So the new stuff, or reasonably new, and that's got ROS Humble on it. They give names to their ROS releases. Then it is connected to a micro ROS implementation of a motor controller, which is pretty cool because it'll accept command val and it'll also output its odometry information. So the Pi can control that over a connection with topics, ROS topics, and so forth. Oh yeah, here you go. And then it's got on the bottom a Ardu Moto, which is a motor controller, which is based on PWM, and a direction line, which is a very standard thing. The wheels each have encoders, and the encoders go into my ESP32 dev board that I've had on various things, including Tightrope Bot, which Camp likes. Anyway,
where's your top hat and your mustache?
Yeah, but see, I didn't need it because this is just a table bot. Then it has a cam, and so
it's awesome, Mark.
On it. And hey, look at that! How about that? Okay, so let's see. We're going to be doing that. So it'll be that direction. All right. So once I get that going, but right now we're running an agent to talk to the MicroROS instance on a little embedded card on one window. And then we're going to run a LiDAR node. So I got the regular LiDAR node for LD19 Leishon LiDAR, which is a nice little cute little guy on top with the blue lights flying around and so forth. So that's now publishing information on ROS topics. And if we run RViz, now I gotta look over the back here. But if we run RViz, you can see the basic pattern that is typical of, well, you can't hear because I guess it's all reflecting everything. There, you can sort of see it there. So if I put my hand in different places, you'd see the outline of what the LiDAR sees showing up on RViz. That's in case folks here are not used to that. So we'll stop that. And then we'll do a quick look at the camera node. So now we're running a USB cam. I couldn't get the ArduCam TOF running. That'll be for next time. That's the cool camera because I won't even talk about that. It'll waste part of my time. So, but anyway, it's a neat little camera. I hope to get that running next time. And then
Marco has it running.
actually, I've been talking to him. It's just that I didn't want to try to put that on here and botch the
Just
entire.
saying. Saying.
Okay, so anyway, you can see the cam image here of the room behind us and so forth. I'm not going to show that though, because now we're going to get on with, actually, I'm going to put this over here and I'll be off screen. And that's because I'm going to have this thing use the LiDAR, and the LiDAR will detect when we get close to the end boundary.
Do you got
And
anything
then,
up your sleeve?
We're going
You don't have anything
to,
up your sleeve, do you?
yes, nothing up my sleeve.
Check his sleeves.
See, nothing up there. It's actually back a ways, so you can't see it. But anyway. All right. Okay, so now I have a script that's going to run. We're going to go for the Gusto. The first version of this was on back in mid-COVID. I showed this thing before it went to ROS 2 and all that. It was still on ROS 1. I showed it go back and then back up to get the other side. Now it's going to, better turn on the motors. Okay. Now it's going to go detect that it has to turn around because it's actually looking at LiDAR data. And there's a little display on here that shows me the rotation and how far I've gone and the speeds and so forth, which we can't even try to see on a camera. So if you want to see it later, you can do that. But we're going to do the mode of this thing where it tries to drive with a Python script. Oh, I accidentally started a second instance of the LiDAR. We shall see if that causes us grief in just a moment. But I stopped that. So now I'm going to start the Python script, which is operating under ROS, has all the topics, it sees what the LiDAR sends in, it looks at all the LiDAR angles and so forth, and it's going to distances and so forth. And I'm going to put it in the mode where it's going to try to turn around when it gets close. So this is the kind of the official part of the challenge. Now it's using the odometry from the micro ROS controller to do a 180-degree turn and go back to the other side and do the same thing there. So it would be nice and happy probably doing this for a while. But I just now today added another mode which may not work. So it's the
That's a phase one.
Yeah, there's phase one.
Okay, and you're 2
So what I
minutes
have
over.
to do
Go
now
ahead.
is I'm going to be stopping it. And suppose you have some horribly dangerous thing that is near you, and you kind of want to see where it is. Okay, so that's the third part of the demo. I'm going to stop this script, and I have to start it now with the version of the code that is capable, hopefully capable of, let's see, what option did I use for that? Ah, yes, F. Okay, so we're gonna go back and forth, and I think I'm gonna stay close to this edge, go back and forth. After this, after the third pass, it's going to look for this guy. And I've never even tried this yet. With some luck, it might actually turn towards it, and then I exit the script. So this is our push goal. We've already done the table challenge.
We'll test it in battle.
So let's see. I think I decided that it's going to go this way, and then it has to.
You're 3 minutes over, but I don't
I think
care.
This guy has to be over here for the demo. So here's the bad guy. This has to be in front, otherwise we don't turn around. Now we're going to get to the exciting part. The odometry is a little bit off here. It's going a little too far, but we've already actually passed the challenge, so it's legal for me to tweak it a bit.
It's all about the show.
All right, so let's see. I'm not looking at the screen now. I don't know if, hey. Yep. Okay, that happened real fast. It turned around. Once it turns around on the third time, it looks at the LiDAR, it finds something about this height, and then it turns towards it. So more to come, but that's basically it for right now. The idea would be approach the thing and also do real-time correction, because you see the odometer's a little off. I'd like to, obviously, I know where it is. When I get to here, I'd like to say, oh, wait a minute, I overshot, move back a little bit, and then go towards it and so forth. So anyway, that's it. Droid bot.
That's awesome. Mark Johnson. What else? Do we have something else there local with Maker Nexus?
We have one more here. So it's
All right.
Roman. He's new to the club. And he's just gonna talk for a second about his
Welcome, Rob.
cool looking robot. You want me to be over there? Sorry.
Wow.
So you could see up there what's being done.
So,
Okay, can we have attention for Roman, please? Okay.
All right, well, I'm here to present the first physical build of the Open VMP robot. It existed in a simulated environment and open source for about 6 months.
can you get a little bit louder?
Okay, I'll try. This is the first physical build of Open VMP robot that you can find on GitHub. Works in a simulated environment for about 6 months already. There are blueprints and software for this robot that are published on GitHub, but they get updated as I actually proceed with assembling the robot. You can see that wiring is not complete. Some motors are still missing, but I'm slowly and gradually moving towards the goal. So this robot is designed to be able to walk, drive, climb up a pole or a tree, hang on cables or branches. And it's powered with a lone mower battery. It is equipped with 14 stepper motors that power 12 joints. It has 12 servo motors. Some of them operate the stereo cameras. Other ones operate the mechanisms that allow robots to either dock somewhere, like dock to a garage or dock to a car or a van that carries them around. They also can dock to each other and form a bigger robot. They can get together into a string of robots like a snake, and that would allow them to get on the roof of a house or get over a fence. That's basically it.
I can climb up things.
Yes, it can climb up a pole or a tree, and over on this side of the robot, you can see how the limbs are used to walk. Over here, you can see how they're used to drive. And over here, it shows how the wheels are, once the limb turns around, they can grab onto something as wide as 50 or 60 centimeters. I don't know how many inches, sorry. So, and It can be a tree or a power pole. And it's all Apache 2.0 license open source out there. Looking for supporters, contributors, partners, everything, whatever. If you're interested, let me know.
Will you be around after the formal part of the meeting just to
Sure.
answer questions?
Sure.
Very
Yeah,
cool.
be sure and get the GitHub on the mailing list.
Yep. Okay. I'll share the link.
Very fine. Thank you, Roman.
Roman, thank you. Do we have any other robots in the room? Camp, it's up to you, virtual robots.
Okay. First off, let me share some of the robot Mark Womack, our own Mark Womack, who's not here this evening. He's on vacation. Bear with me. I need to share the screen. These are some images he shared on the mailing list. See if I can find them. Yeah, he's building a Robo Magellan robot. Says he's going to be using ROS, but this is the start of the robot. And here's a look inside of it there. Let's see, he wrote some words. Going to be on vacation, motor controller squared away. He's doing some interesting work with the Teensy microcontroller. You may have seen it on the mailing list. Everybody needs to be on the mailing list, but he's doing some interesting protocol work in there. Let's see, he wants to look back at Lino Robot 2 as a base for defining Casper for ROS 2. Casper is the name of his robot. Still a long way to go. Wants to get the motor controller in better shape. But regardless, this is a look at what Mark Womack's working on with a Robo Magellan robot. Thomas, I think you've got some show and tell, right?
Yeah, I do. I got two things to show today.
I'm gonna start the timer.
Okay, the first thing I want to show for run what you brung is my electronic robot drummer. Now you guys have heard of electronic drums, and well, this set here can play drums all by itself. But I like the idea of something actually hitting the all the pads of the drum here, and so I developed it. It ultimately will have 4 drumsticks when I get more stands for it. But for now, I've got 2, and they're programmed with a very simple drum beat. They run off an Arduino with a little interface board, and pretty simple, and it works. And I was worried about compliance, so I am using rubber bands here, both here and on the drumstick, so I don't overdrive the servos or break the drumstick or break anything. And it all works fairly well. So without any further ado, let's get it drumming. And that's my phase 1 drummer. If we had a drum a drum thing, I would win first place for it. But there's more to come.
Hard to impress, but easily amused.
And yes, that should amuse at least 2 or 3 of you. Next up, a few months back, we introduced the AI challenge, which is still not on the website. So one of these days, we got to add that. But I am ready for phase 1 of the AI challenge, and I'm going to post the AI challenge into the chat so people know what it is. You think with all my work on AI and robotics and all that, I should be at phase 3 by now, but not all in one package. That's to come. There's the AI challenge. I just threw it in the chat for everyone. This was okayed and thumbed up by Camp. So
Yeah, I thumbed it up.
he thumbed it up. It's not the right word, is it?
It's
Oh,
your 5 minutes. It's your 5 minutes, dude.
all right. So here we go. I'm going to share my screen. We're running Cynthium here, Cynthium Arc. And I would ask that everyone would mute their microphones because this is going to pick up every sound because I'm running it from the same computer that I'm talking to you through. Let's see, share. There we go. Share screen. Share the right screen, not the wrong screen. I've shared the wrong screen before. That's embarrassing. Okay, so this is Arc Cynthium, Cynthium Arc. This has the Bing speech recognition. And OpenAI, it's using GPT-3 model DaVinci 2. And I've loaded it with a seed personality here. This is for my robot Betty 9, who's actually behind that green partition in the back. So without any further ado, let's attempt phase 1, chatting with an AI. Good evening, how are you?
I am doing great, thank you for asking. I hope you have had a good day as well.
I did. What did you do today?
I spent the day doing some research on my upcoming projects. I also worked on some coding projects and had a meeting with my professor about one of my papers. In the evening, I went for a walk with my dog and then...
What's your dog's name?
I don't really have a dog. I was just making an example.
Why did you lie to me?
I am sorry if I misled you. I was just trying to make a point about how I spend my day.
Well, tell me about your class today.
Today in my artificial intelligence class, we discussed a few upcoming projects and deadlines. We also went over some of the papers that we will be writing. I am really enjoying the class so far and learning a lot.
What's your professor's name?
Mr. Smith,
How tall is he?
I am not sure, but he seems to be at average height.
What do you like about your professor?
I enjoy the way that he lectures and the material that we are covering in the class. He is also very helpful and available to answer any questions that I have.
All right, that's the end of the demo there. Did that come through, guys?
Very nice. That's a phase 1 AI challenge, Thomas.
Phase 1 AI challenge.
And we'll get that on the challenge page.
Now I got to get to phase 2. Asking the robot to visually identify an object in the room. And that would be kind of like, do you see a cat in the room and then it's got to say where it is on the left or the right? I'm a little bit unclear about how that would work, Cam.
Well, it's purposely vague to help enhance creativity.
Well, there you go then. Thank you, Cam.
I do have a BS degree. So. All right, who's next? Anybody else online have a show and tell for the challenge? I've got a video to show. This is actually Mike Ferguson doing his thing at Maker Faire, and it's probably the best table bot challenge I have ever seen. And this is Jim, I think you made this video. Let's see here. Jim D'Annunzio, ladies and gentlemen.
Yeah, the one from Robo Games.
Let's see if I can get some audio. Hang on.
Hey, Jim, you have a phase 1 AI. You should do that one too. You should show your AI guy.
Yeah, I was just thinking about that. Maybe I'll just show the video though, because instead of live. We're not hearing audio though. I don't think you shared audio.
Yes. So there, Mike just did a phase 3. He angles the robot a particular way, and it'll do a phase 2. He's using that LiDAR. The LiDAR not nods. Can you guys hear me? Hello, test 1, 2.
Yes,
Can you hear
yes, we hear you.
me? Okay, thank you. Can you hear the video? I don't think you can hear the video though.
No sound in the video.
All right, I'll just narrate it. The last one here, he's going to do a phase 1, I believe. But the point is that it does 1, 2, and 3. He's 3D printed the whole thing, and he's got a nodding LiDAR there, and it's really sensational. Hopefully, he doesn't do a phase 4. So that's probably the best TableBot challenge I have ever seen.
Yeah, that was great. And he has a web page that he posted about the details of about that project.
Yeah, his
Which
his
is, yeah.
blog is Chisel and Robot. I think you can just Google that Chisel and Robot and find out. I'll Google it. Hang on. Stuff by Mike Ferguson. All right, who else has a show and tell for this evening?
I can do one if you want to see my digital avatar. It's similar to Thomas's thing.
We'd love to see your digital avatar.
This is a pre-recorded. I'm not going to do live, but that should be sufficient for today.
Yeah, yeah.
All right. Oh, let me.
He brought it to the barbecue. It was great.
Yeah, I'm still definitely working on this, and you know, I put some time into it over the past few weeks, improving a bit here and there. All right, here, let me play this. I won't do the intro of my, or I guess, I don't know, how long is this?
Did you share the sound, Jim?
What's that?
Did you share the sound?
Yeah, it should be, you should be able to hear it. Let me know if you can't.
I am Cooper. I am an art.
Hold on a second.
Turn up the volume.
Hi, I am Cooper. I am an artificial human ready to chat with you. I have a background in software engineering and robotics.
You can hear it? All right.
Yeah, he's pretty creepy.
My name is Jim. How are you doing today?
But at least he blinks. He's kind of slow, but sorry about that.
Hello, Jim. It's nice to meet you. I'm doing well. Thank you for asking.
There we go. Phase 1.
A rough day at work coming back from vacation.
So here I channeled the Eliza, you know, kind of from 40 years ago.
I'm sorry to hear that, Jim. Would you like to talk about it? Sometimes it can be helpful to talk about what happened and get things off your chest.
Sure.
That's
I came
good,
back
Jim.
from vacation and there was a lot of stuff to clean up. And the guy who was there before went on vacation.
So you can see up here is the text that's happening, like it heard me and now it's replying. The rest
I
of the,
can understand why that would be frustrating. It can be hard to come back from a vacation and feel like you have to play catch up.
He's clearly Italian. He has to
Yes,
talk with his
definitely.
hands.
So, what do you like to do in your spare time?
we already know he's a hobby roboticist, but he's,
As a hobby roboticist, I love to build robots and tinker with electronics. I also enjoy hiking and exploring new trails, reading science fiction books, and attending various events and seminars related to robotics and software engineering.
and he's a software engineer.
That sounds just like me. So,
That's great, Jim. It's always nice to meet someone with similar interests.
so what do you think of Sophia from Henson Robotics?
So yeah, this is in the database, so, or in the, the model, so he knows.
Sophia from Hanson Robotics is definitely an impressive piece of engineering. It's fascinating how she uses computer vision, natural language processing, and machine learning to interact with people. However, I do believe that we still have a long way to go before we can create truly conscious robots. Nonetheless, Sophia is a great example of how far we've come and how much potential there is in the field of robotics.
But isn't she mainly controlled by humans behind the scene?
This plays an idle animation, so it's kind of, repetitive, but I need artists.
Yes, that's correct. While Sophia is capable of processing information and generating responses on her own, she still requires human programmers and operators to control her behavior and responses. However, this should not take away from the incredible technological advancements that make Sophia possible.
I know Thomas was impressed with Sophia.
So what kind of projects do you recommend for intermediate to advanced roboticists?
There's little things like it's even a pain to make it cut off at a sentence, end of a sentence, because the AI models, you have to search for
As
the
an
period.
experienced roboticist, there are many exciting projects that you could consider. Here are a few ideas. 1. Autonomous drones for agriculture. Develop drones that can collect data about crops, identify problem areas,
Is that my time?
and make recommendations for farmers.
That's it again.
2. Smart home automation. Create a smart home system that can automatically adjust settings like lighting and temperature based
And we can skip here too.
and interact with humans in a natural way. 4. Self-driving cars. Develop an AI system that can drive a car autonomously, without human intervention. 5. Augmented exoskeletons. Build an exoskeleton that can assist people with physical disabilities, allowing them to perform activities that were previously difficult or impossible.
Well, this
All
has
right.
been great, Cooper. Thanks a lot. I'll see you next time.
Oh, this is the end here.
You're very welcome, Jim. It was great chatting with you.
There
Jim,
you have it.
thank you very much.
Oh, I do have my camera on. Thank you.
What else? What else? Do we have another show this evening? One more? One or two more?
You can unspotlight me.
Yeah, let me do that.
Oh, I can do it myself.
Is it done? All right. Let's have one more look at Robo Games before we call it a night. This is Robo Games featuring Ralph Hips and Nathan. I can't think of his last name, but he's a club member and he actually managed to touch the cone. Jim, this is your video again. Thank you.
Oh yeah, no problem. Yeah, you can point to all of my video. Yeah, I took a bunch of videos of the Robo Games. They're all on my YouTube.
Blackbeard. It's been sped up a little bit, but this is at Robo Games just a couple of months ago.
That's the best part.
About a 3-minute video, and then we'll call it a night. That's the trap cone there. Ralph, I think you got bronze medal and ended up like 12 feet from the goal. Am I right?
Something like that, yeah.
17, wasn't it?
Sorry.
We'll see it here. Robo Magellan's contest where you're given a GPS coordinate and an orange cone is placed and the robot has to traverse like a 100-yard playing field and touch the orange cone. There's the orange cone there. I think he gets a look at it and goes wide left.
Yeah, the best part was I ran into pretty much everything but the cone.
But you got close. And you got the bronze medal, the happiest medal of all. So Robo Magellan's a really good contest with a full-scale robot, and it's not a combat robot. And I think if you could build something that can reliably get to a particular GPS coordinate, even if it is 12 or 15 feet off, there's where we stopped it. And then this is the Chinese, Hong Kong University, excuse me.
Or some people used just Dead Reckoning. Wasn't it Ralph's?
Well, I think Bob Allen may have had Dead Reckoning, but
Or is it Bob's? Bob Allen, yeah.
he's still out there. But it's because he didn't have it. You got to work with what you got on that day.
Or what about the solar compass? Wasn't that is that Bob's? I can't remember now. Solar compass.
That was my thing, solar compass
Yeah.
and wordometry.
I can't. Kind of too quiet there.
So these guys got the silver medal, I believe. They're going to get a little closer to the gold cone. And then finally, this is Nathan touching a gold cone. That's the easy gold cone. I meant to say the bonus cone, but there's cones along the way that you can touch that give you a fractional multiplier. That's an easy one there. It's like 0.9. So we take 10% off your time, decreases your run time by 10% if you take time to touch that. Now this one I call the trap bonus cone, and that gave you like 50% off. I mean, if you took your time and actually touched that one and then hit the gold cone, it subtracts 50% off of your time. If you don't touch the gold cone at the end, your score is your distance from the gold cone. There's no timing element to it. There was another really tricky cone tucked way back in the corridor there where the dumpsters were. If you touched that one, it was like 0.1 multiplier. It decreased your time like 90%. But there's your gold medal run there. That's Nathan, should be able to think of his last name, actually touching the gold cone there. Yay, Nathan.
That was really great. Yeah, I talked to him a lot.
That was awesome. All right.
I want to enter that contest next year.
There's show and tell out there for this evening. All right, this has been a lot of fun. Thanks to Mark Rose for the special presentation on the VIPER mission. Thanks to everybody participating in the HBRC Challenge Phase 2 21st Annual. And thanks for everybody attending our Homebrew Robotics Club General Meeting. Next meeting is going to be our business meeting, the first Wednesday. So that'll be, July 5th. And we have, everybody's on the mailing list. We have a weekly Ross discussion group. We have a bi-weekly voice intelligence group. And keep building those homebrewed robots. Motion, the meeting be adjourned. Motion carries. Good night. Good to see you, Carl. Good to see you, James, Thomas. Walter, yay, you made it. You're muted.
Have a good one.
For a little bit. Have a good night, guys. We'll see you.
Take care, guys. Good to see all of you.
Fun. Love you.
Okay.
Hey, anybody there still at the Maker Nexus? They may have already packed up. I was curious how many people were there. Must have been about 10 people. Well, that was some contraption that guy had out there, though. What was it? Climbing trees and stuff, supposed to?
Picking apples, I think it was gonna.
Yeah.
Oh.
No, that was quite an apparatus. All right. Well, we had some fun. Stephen, good to see you. You're on vacation, right? He must have had his bot dial in. Jeremy, see you next time. Neil, Jim, thanks for the show. That was good. Thomas, we'll
Yeah,
see
I
you
hope
next.
it wasn't too creepy.
Yeah. Well, it was a little bit creepy, but that's okay.
A little bit better. I'm into the uncanny valley with Thomas now.
Yeah.
Trapped in the uncanny valley.
Right.
Except
Sorry.
mine goes away when you turn off the computer.
And mine still sits in the corner of the.
I bought a Hero. I built a Hero Junior that I built home from California when I was there, and he wakes me up every morning, and periodically he just starts spouting off nursery rhymes and stuff. He's really funny. But I love those spots from the 80s.
Oh.
Hey, Jim, did you see that email I sent you about maybe having your robot read a book or look at his cell phone? Can you program that kind of hard, video into the video? Can you add objects into his world?
Oh yeah, I haven't read your email. I kind of I saw briefly because it's in the homebrew. I think it was CC'd to Homebrew Robotics, right? So
Right.
I
Yeah.
put those. I get a digest, but I think I briefly saw that. I'll have to read it. But yeah, with some work, you can put props and everything into that environment. The hard part is the animation. Anyway.
Have you started recording?
Oh, no.
Okay. You can stop recording now. That's fine.
Yeah,